Hi, I'm Muchen from Northwestern University. I would like to introduce our work, Move Beyond Trajectories, Distribution Space Coupling for Crowd Navigation. Robots navigating in dense human crowds need to properly leverage the cooperation from other humans. For example, if the robot knows other humans will make space for it, it can plan a much shorter path while being safe. A common framework for such social navigation tasks is coupled prediction and planning, hereinafter referred to as CPAP. A typical first step for CPAP is to identify a preference distribution over trajectories for each agent, which represents the individual navigation task. Then, an interaction function, which evaluates the risk of joint trajectories from multiple agents, will be introduced. Lastly, based on the preference distribution and the interaction function, a conventional CPAP algorithm will find joint optimal trajectories for the robot and other humans. However, using a single trajectory to represent human intent means the robot plans its future trajectory while expecting other humans will go exactly as predicted, which is rarely true in reality since the ambiguity in human behaviors. In this work, we use the preference distribution to model human intent and capture the evolution of agent preferences. This helps the robot to make a decision without knowing the exact future actions from other agents, but instead reasoning over all possible future actions. Let's start with a toy example, where we have two agents with their trajectories in a one-dimensional space. Their original preferences are shown in the figure below. First, we use the joint expected value of the interaction function to represent the joint expected risk between the two agents. Then, we use the KL divergence between the same agent's preferences in different iterations to represent the preference deviation. Now, we can formulate the problem as finding optimal preference distributions for the two agents, which minimize the joint expected risk while regularizing the preference deviation to preserve the original preferences. Furthermore, we use iterative best response to update one agent at a time and assume the rest of the agent's preferences are fixed during the update. Therefore, in each iteration, for each agent, we have a sub-objective, which is a summation of the joint expected risk and the agent's own preference deviation from the last iteration. For the sub-objective, we can find an analytical solution for the global minimum and use it as the update rule to optimize each agent's preference sequentially. And we prove that this update is guaranteed to reduce the joint expected risk, and the reduction is bounded below by the preference deviation. In other words, a larger preference deviation will lead to safer joint preferences. And the above results also hold with arbitrary types of distribution and arbitrary numbers of agents. However, when working with high-dimensional trajectories, computing the update becomes intractable. Therefore, we proposed a sampling-based motion planner, DistNav, to approximate the update rule through Monte Carlo integration. We use Gaussian processes to identify each agent's original preferences, but no offline training is used. We first evaluate our algorithm on a highly dense and interactive subset of the ETH pedestrian dataset, which is further divided into 181 test runs. In each run, we took out one pedestrian's trajectory and used the same start point and destination for the robot navigation task, so we can compare our method with human performance. We also compare DistNav with conventional motion planners, trajectory-based CPAP methods, and several reinforcement learning-based methods. Our method outperforms all of them on the navigation safety and efficiency metrics, and is competitive with human performance. We complement the ETH study with two simulated evaluations, where we created 5 and 7 simulated pedestrians using optimal reciprocal collision avoidance algorithm. This is a common testing environment for deep reinforcement learning agents. We show that our method, which doesn't require training, either outperforms or is competitive with other deep reinforcement learning methods, which are trained in the same environment. Combined with the ETH study, we conclude that our method has better safety and efficiency performance in the social navigation task. Thank you for watching, and more details about the method and experiments can be found in our website.